If you think of a simple linear regression model with intercept alpha and slope beta, well, except the trivial case of beta being 0, then the response variable, the y variable, can take, in theory, unboundedly large values positively or negatively. If beta is positive, then if the x value tends off to infinity, so will the y. And if the beta value is negative, then as x tends off to infinity, the y will tend off to minus infinity. Now, of course, that doesn't really describe a lot of variables. Sometimes we know the response has to be strictly positive or strictly non-negative, or very often we might have a count that might mean how many times did this outcome occur, so 0 times, or 1, or 2, or 3. So we want to model response types that aren't just a continuous value on an, in theory, infinite interval. So another example might be even simpler. Will this outcome happen? A simple yes or no. Survival of a patient in a hospital, either the patient lives or the patient doesn't live. There's only 2 outcomes, and I want to know how likely one is relative to the other. And all of these problems we can actually tackle through a similar approach to linear models, but a generalized linear model, or GLM. So GLM starts with the idea of a standard linear regression model, but also has a link function, which is exactly how it sounds. It links the output of a simple linear regression model to another function which will deliver a response variable of the type appropriate if I've selected a reasonable link function. If I'm trying to predict a yes or no, a binary outcome, if I say the outcome happening is a 1 and the outcome not happening is a 0, I just simply want to predict for which combination of the predictors do I think there will be 1s, and for which combination of the predictors do I think there will be 0s, and indeed the likelihood, the probability of 1 rather than 0. So what I want to do is I want to transform the output of a simple linear regression model, which in theory could be minus infinity up to infinity, into something on a scale that's between 0 and 1. So basically telling me how likely do I think it is to be a 1 instead of a 0. Now there are many actual possible link functions here. We will cover probably the 2 main ones, the logit function and the probit function. So just before we get to either of these, the logit of a probability, where the probability p is strictly between 0 and 1, is defined. Logit of p is the natural logarithm of p divided by 1 minus p. So what we have is that as p gets close to 0, then p over 1 minus p also gets close to 0, and so the logit function tends off towards minus infinity. At the other end, p over 1 minus p diverges off to infinity as p tends to 1, and so its logarithm also diverges off to positive infinity. So the function looks something like that. Obviously I've truncated the graph, but it sort of gets infinitely steep towards 0 and towards 1. So if I were to run a regression model and I wanted the output to be between 0 and 1, I can sort of invert this graph to say, well, I'm predicting a score between infinity and minus infinity up to infinity, and converting that into a probability between 0 and 1. So I would do this by inverting the logit function. If we have an observed data set with some observed predictors, so I can say, for this set of predictors, the outcome did happen. For this set of predictors, the outcome didn't happen. For this set of predictors, the outcome did happen, and so on. Then what we want to do is we want to sort of work backwards to fit which combination of the predictors best explained why the outcomes were ones rather than zeros. And we do this via the inverse of the function that we saw on the previous slide. This is just a reflection of that, and this is the inverse of the logit function. So you can see that it asymptotes off towards 1 as the horizontal axis tends to infinity, and at the other end it asymptotes down towards 0 as we tend to minus infinity. If I just invert the logit function, if I invert the natural log of p over 1 minus p, by all means check my calculation here, but what we get left with is we get a probability which is e to the y divided by 1 plus e to the y, where y is this logit function of p. So what that actually means is I want to be trying to fit a value of y through a linear regression model to best match, so that this will give high values of p, high probabilities associated with the points that I've observed as ones, the ones I saw happen, and low scores when I've observed zeros. So it still is a linear model, so I can actually take linear combinations of those predictors, whatever they would be. So in reality, what I have is I have a whole load of points with a 0 and a whole load of points with a 1, and I can move those around slightly, because if my y is the output of a linear regression model, then maybe I increase beta, so I increase the size of y with each change in x, or maybe I increase alpha, I shove them all along or back a little bit. So what I'm left doing is I'm taking, you can see I've superimposed some points here, this is just totally made up data, but I'd be shuffling these points around, linear combinations of things I've observed, to try and best get the gap between where these points sit, and they will all sit at either 0 or 1, either the outcome didn't happen or it did, the patient died or the patient survived, the thing was a failure or the thing was a success. But I can move around these points, linear combinations within my y, to best explain this graph. And we'll see a little bit more of that in the next video.